Welcome to the fifth lecture on advanced mechanics. Today we're going to see how what we've already learned in the past few lectures can be implemented in some practical examples. We're going to talk about formulation and solution strategies. Learning objectives are knowing how to combine and reduce the basic linear elasticity equations, learning analytical solution strategies for 3D problems with simple geometries, and understanding the assumption required for derivation of the displacement formulation. We're going to talk about these three examples. A pressurized hollow sphere under internal and external pressure, a cube under uniaxial loading, and a prismatic bar under axial loading, which is basically its own weight. The first part of the lecture is about linear elastostatic equations. Okay, let's review some equations that some of them we've already seen. Can you identify equilibrium equations here? So equilibrium equations deal with the balance of forces. Can you identify constitutive laws? Constitutive laws deal with the relation between a stress and a strain. So basically, Hooke's law. What about compatibility constraint? I know that you've not seen this before, but we're going to use it in some of the solutions. It guarantees that we achieve unique solutions for our problems. And finally, kinematic relation. That's the relation that relates strains with displacement. Yes, that's it. Okay, what are the following quantities? We have sigma, it's Cauchy stress tensor. We have delta, that's chronicle delta. We have epsilon, which is our small or infinitesimal strain tensor. We have lambda and mu. They are Lame's constants for isotropic material. We have u, the displacement vector, and p, which is body force per unit volume vector. And you may remember that you can relate that with body forces through the material density rho. Basic linear elastostatic equations. Here we talk about the basic equations we use to solve practical examples. First is equilibrium equations. You've already seen linear momentum, which balances stresses in the material with body forces. And here we show angular momentum, which is basically guarantees symmetry in the stress tensor. Then we have kinematic or strain displacement relations. As I said before, it relates a strain with displacement. And here you see it for infinitesimal case. Then we have constitutive or material laws. Basically, these are the laws that relate a stress and a strains together. We've already seen that for isotropic material based on Lame's constants. This is the relation for a stress based on a strain. And here you see the inverse relation for a strain based on a stress. In total, we have 15 unknowns. We want to find the displacement field in the material, how the body particles moves. We want to know the strains, and we want to know the stresses. The displacement field is in 3D space, so we have three unknown displacements. For the strain and stress, we know these are second order tensors with 9 elements each, but we know only 6 of them are unique because of symmetry of strain and stress tensors. So we have 6 unknown strains and 6 unknown stresses. And note that all of the above equations are linear in terms of the unknowns. That's the benefit of working with infinitesimal or small strain. Okay, also note that we can have the constitutive or material law in the engineering form based on elasticity modulus and Poisson ratio. You see that both for the relation for a stress versus a strain and a strain versus a stress here. Okay, let's see if we have the 15 equations, independent equations, for the 15 unknowns that we have. Okay, the linear momentum gives us 3 equations. So you know that we have J as a summative index. So the only free index is I, and I can have 3 values. So this equation gives us 3 equations. If I want to expand it, it's going to be sigma 1 j comma j plus p1 equal to 0, sigma 2 j comma j plus p2 is equal to 0, and sigma 3 j comma j plus p3 is equal to 0. So these are the 3 equations we get from linear momentum. And note that this is J is a it's a summative index. So for example, for sigma 3jj plus p3 equal to 0, if we expand it, we get sigma 3 1 comma 1, which I'm going to write it in terms of partial derivative. So it's going to get partial sigma 3 1 partial x1 plus partial sigma 3 2 partial x2 plus partial sigma 3 3 partial x3 plus p3 is equal to 0. And the same we have it for the other 2 relations. So there's our 3 equations from the linear momentum relation. Then from the kinematic or strain displacement relation, we get 6 equations. How? Because we have I and J, both of them are free indexes, and we know epsilon is a 3 by 3 a second order tensor, so it, with 9 elements, but only 6 of them are independent. So basically we get 6 independent equations from here. If I want to expand it, we're gonna get epsilon 1 1 is equal to u 1 1, which is basically partial u partial u1 partial x1. We get epsilon 2 2 equal to u 2 2, epsilon 3 3 equal to u 3 3, epsilon 1 2 is equal to 1 divided by 2 partial u 1 partial x2 plus partial u 2 partial x1. We get for 1 3 is half of u1, 3 plus u3, 1. And for epsilon 2, 3, we get half of u2, 3 plus u3, 2. Just pay attention that epsilon 3, 2 is equal to epsilon 2, 3, epsilon 3, 1 is equal to epsilon 1, 3, and epsilon 2, 1 is equal to epsilon 1, 2. So we get only 6 equations, independent equations here. Okay, and from constitutive law, we get another 6 equations, because again, we have the stress tensor. The stress tensor is a second order tensor with 9 elements, but only 6 of them are independent. So again, if I expand it, I end up with relations for sigma 1, 1 and sigma 2, 2 and sigma 3, 3, and also sigma 1, 2, sigma 1, 3 and sigma 2, 3. And that's our 6 relations here. Okay, that's it. So we already have 15 equations. Then we have compatibility constraint or Saint-Venant compatibility equations. You see it here. It gives us 6 equations, but we're going to see more about the equations it gives us and Saint-Venant principle later. And finally, we have traction boundary conditions or displacement boundary conditions. Each of them gives us 3 equations. So you've already seen the traction equations. So it basically gives us a vector relation for the traction. Note that J is a summative index, so we have J1 and 1, T2 is sigma J2 and 2, and T3 is sigma J3 and 3. And if I want to expand one of these, you get, for example, T1 equal to sigma 1, 1 and 1 plus sigma 2, 1 and 2 plus sigma 3, 1 and 3. And note that we used sigma 1, 1, 2, 1 and 3, 1. That's basically they are basically a row in the sigma that's basically a column in the a stress tensor sigma. Okay, for the displacement, again, it simply gives us 3 sets of equation. It says that displacement in each of the directions is associated with external displacement at the boundary. So U1 equal to D1, U2 equal to D2, and U3 equal to D3. The 3 equations here, the 3 equations here. These are actually our constraints to find all of the constants coming from integrating the equilibrium, kinematics, and material law equations. Okay, a bit more about compatibility equation. And if we expand it and get rid of all of the symmetric components, we end up with 6 unique equations here. You see that we have twice partial to epsilon 1, 2, partial x1, partial x2, equal to partial to epsilon 1, 1, partial to x2, plus partial to epsilon 2, 2, partial to x1. The same we have it for epsilon 2, 3 and epsilon 3, 1. And for partial to epsilon 1, 1 over partial x2, partial x3, we get partial to epsilon 1, 2, partial x3, partial x1, minus partial to epsilon 2, 3, partial 2x1, and partial to epsilon 3, 1, partial x1, partial x2. And we have again the same for epsilon 2, 2 and epsilon 3, 3. So in some of the solutions, you have to enforce these equations as well. So you make sure that you get a unique solution for your problem. Let's start with boundary conditions. These are the conditions to be satisfied on the boundary surface S and will appear in one of the following statements. It can be displacement prescribed everywhere. Basically, we know the displacement of body surface. Here we have U asterisk, and asterisk means it is prescribed. We know it. Or it can be traction prescribed everywhere. Ti equal to Ti asterisk, meaning that we know the stress on the whole body boundary condition surface. Or it can be displacement prescribed on portion of the boundary condition surface, S1, and traction prescribed on the remainder of this surface, S2. So basically the boundary surface is S. We know that on part of it, S1, the displacement is prescribed, and on the rest of it, S2, the traction or stress is known. Okay. Remember the relation between traction, stress, and normal vector to the surface. We're going to use it in a few examples later. Then here are the main assumptions for problems that we deal with them based on elastostatics. First, inertial forces are neglected. So we don't care about acceleration terms. All displacement gradients are small in comparison to unity. Note that we're talking about displacement gradients. But there is no restriction on the magnitude of displacement. So basically, the displacement gradients are small, so we have infinitesimal strain case, but we may have large deformation because there is no restriction on the magnitude of displacement. Basically, it means we can use the infinitesimal strain tensor to characterize deformation, and also we don't need to distinguish between deformed and undeformed configurations because they're almost aligned with each other. And finally, the material is an isotropic linear elastic solid with Young modulus E and Poisson's ratio nu. And on the St. Venant's principle, it basically says a stress and a strain reasonably distant from the point of application of external force are not significantly altered if the applied force is replaced by a statically equivalent load. That means, assume these 3 bars. This one is under uniform load. This one is under concentrated load. And this one is under point loads. Close to the point of exertion of the load, you see that the stress distribution is very different. Here we have 2 peaks. Here we have a peak. And here we have a constant stress distribution. But reasonably distance from the point of application of the load, the stress distribution is uniform, as if the loads are equivalent. So basically, if we find a distributed load or a partially distributed load that gives us statically the same value as these 2-point loads, and we look at a stress distribution far away from the application point of the load, we don't see any difference. That's basically Saint-Venant's principle, and the compatibility constraints are kind of related to that. We don't go into details, but basically, in other words, the difference between the effect of two different but statically equivalent loads become very small at sufficiently large distance from the load. Okay, that's it for the first part of the lecture. We're going to continue after a short break.